Dzień dobry, jestem Gabriel Volpe z Argentyny, ale mieszkam w Japonii. Mało mówię po polsku, bo polski jest trudny. Może następnym razem przedstawię wam moją prezentację po polsku, ale tym razem to musi być po angielsku. Don't worry. Don't worry, the talk is gonna be in English. I just wanna use this opportunity to try my Polish skills. Hope you guys understood. Anyways, let's rewind. My name is Gabriel Volpe. I'm a software engineer at Paydi in Tokyo, Japan, and I came all the way to this beautiful country to speak about functional programming and specifically about MTL, classy optics, the real monad, we're gonna get there, and Tagless Final. So let's get started. So what's MTL? MTL stands for the Monad Transformers Library, and it basically allows you to encode effects as type classes instead of using data types. And I consider it a sane alternative to monad transformers, and specifically in Scala, where we can suffer from performance issues, we can optimize such instances at the end of the world, and we can avoid using transformers at all. So let's see some examples. This is a program that allows you, well, I'm using the monad transformer state t, which allows you to thread states sequentially. And if you pay attention to the return type, it's state t of f of string, meaning that we are adding the capability of threading state to this parametric f. And to operate using this monad transformer, we have to operate on using all these state t get, state t lift f, and so on. So we have to lift any arbitrary f computation into the monad transformer stack. And pay attention to the return type. We are just basically committing to using this monad transformer in our function. So MTL, using MTL, you can write the same program and see how this changes. Our return type is now a parametric f of units, and we moved the effect of threading state into a type class constraint. And it's super powerful, and it's very easy. You see that right now we are not using any monad transformer. Our console operation doesn't have to be lifted into any transformer. So we get free of transformers in this case. And I think that's already powerful, and it's more simplistic. So that's already one benefit that we can see immediately. There's another monad transformer called the reader T, or more commonly known as Kleisli in the CATS ecosystem. It basically encodes, it's a data type that encodes a function from A to f of b. In this case, A is appconfig, and f of b is f of units. This basically allows you to carry some environment, some kind of context, right? And the MTL equivalent is called applicative ask. In Haskell, it's called monad reader, but in CATS MTL library, it's called applicative ask, and it only requires to have an applicative. And it's basically the same, right? In this example, I'm just asking for a current environment and basically printing that out into the console after I flat map on the value. I define this convenient method called ask, so I don't have to summon the applicative ask instance every time I want to access the context. And also this type alias has appconfig or has foo kind of syntax to allow me to read better using context-bound constraints. So it is super cool. We've seen two different effects, state and current environment, but in normal applications, you will need to combine different effects, right? And if you were to combine state t and reader t, this is how it looks like. How many of you can understand this code, like at first sight? It's really ugly, and we have only two different effects. The more monad transformers that you add, the uglier it gets, and you also will run into performance issues. And it's really hard to understand the kind of code. You also have to specify all the types because the Scala compiler cannot infer the types. So it's very cumbersome. Even like, take a look at the second line. We are lifting the console put string line into the state t monad transformer, and then we have to lift this whole transformer into Kleisli as well. So it's super painful, and monad transformers are good when you're learning, but then soon you realize that you get into this kind of mess, and it's hard. It's hard to write this kind of code or even read this kind of code. So MTL is immediately much better. And as you can see here, this is the equivalent of the previous program. Our effect constraints are now type classes constraints. We have an applicative ask and a monad state. And we can just operate on that type constructor F. We don't need to lift anything into monad transformers. So I think we can already agree that this is a way better approach. So whenever you can use MTL, go and use MTL instead of monad transformers. So these are the only two effects I'm going to be presenting, but there are many other effects. So I invite you to take a look at the CATS MTL website. There's many examples and documentation. So you might find some effects that are interesting for you. But let's get into classy optics. How many of you know what classy optics are? Wow, that's very, very few hands. And that's great, because yeah, I haven't seen people, especially in the Scala community, talking about classy optics. It's a very common concept in Haskell, and it's basically about lenses. So lenses, the most useful example I ever seen, and probably the simplest, it's when you have a case class with nested case classes, and you want to access or modify, let's say, a field that it's like 5 levels deep, and you can define a lens to do that for you. And then the power thing about using lenses is you can compose lenses with other lenses, also with prisms, and just reuse them in different applications. So it's basically a first-class access for product types. A case class is basically a product type. Prisms are very similar, but they operate on some types or co-product types. So for example, if we have an ADT in Scala, normally represented using Siltrate, case classes, and case objects, a prism will allows you to select a single branch of this ADT, which is super cool, and they compose as well. And whenever we can associate with each type, a type class full of these optics, for that type, we can say that we have classy optics, or we can be more specific and say we have classy lenses or classy prisms. So from now on, when I say classy lenses or classy prisms, I might be more specific in just using lenses or prisms. So in Scala, we have this fantastic micro library called MeowMTL, written by Oleg Pishkov, and it has instances for CATS MTL and CATS effect. And it's a wonderful piece that it's not very well known and it's not super used. But I hope many of you will give it a try after the examples I'm going to show. So I defined this case class appconfig with 2 other case classes inside. So it's a product type. I have a nested case class of configurations. I define these type aliases for the applicative ask of F and the different kind of configurations. And again, this a convenient method called ask, so we don't have to summon the instance every time. So with all this machinery in place, we can write software like this kind of polymorphic code. So going back to the applicative ask type class from MTL, we see 3 functions here, 1, 2, and 3. They basically do the same. They ask for the current environment, they flat map, and just print it to the console. So it's very, very trivial, very similar. The only difference, it's the kind of data they can access to. So if you, the function number 1 can access to the whole thing, but number 2 and number 3 are a bit more restricted. They can only access a single case class inside this appconfig. So this is one amazing way to constrain your functions. Let's say you're reading configuration with AWS credentials, Kubernetes credentials, and so on, and you just want to share one specific type of data with a function. You don't want to share the whole thing. So this is one way to achieve it using the applicative ask type class. And I think it's very powerful. It's really nice. When we have these instance functions, we are invoking 1, 2, and 3, and we can see that we can only satisfy number 1, the first constraint, but we cannot satisfy 2 and 3. And so the Scala compiler will complain and will not compile. It can't solve this implicit applicative ask for function 2 and 3. And this is where classy lenses come to the rescue. And just by adding this single import, this code will compile and it would work. How does it so? Well, it's smart enough to recognize that we can satisfy the first constraint, applicative ask of f and app config. And by adding this single import, the library will actually create two lenses for these other specific type classes, for the case classes, the configurations, and it will derive the applicative instance for us, the applicative ask instance. And if you look at the implementation, this is how it looks like. You can probably understand, because it has a parent that is the applicative ask instance that we have, and given a lens to access, to zoom in into the data structure, it can actually just map by asking the parent and just using the lens to get access to that particularly case class in this case. I think this is super powerful. You don't really need to understand this. Like if you understand that you can get the instance derivation just by a single import, that's enough. To be honest, I've been using this without even understanding this library. I had to study to give this talk, to be honest. But let's look into another example. Monad error type class from CAT score. In this case, I'm defining a hierarchy of payment errors. Extends exception because we want to be compatible with CAT's effects and the CAT's ecosystem. But ignore that for now. And given this error handler interface, which encapsulates a monad error and a handler that is a total function that we have to define, and a default implementation for handler errors, we can define a payment errors handler. And this is one way to implement it. For example, defining an object payment error handler with an apply that requires a monad error for F and payment error. So we are being specific about what kind of error we want to handle. All we have to do is just define this handler, which is a total function again, and we are only printing the message out into the console. It's not very useful, but it explains the case in a very simple way. The cool thing about this, having a total function, is that tomorrow we will probably add a new error type into this hierarchy, and this code should not compile if you have the right compiler flags. But at least you're going to get a warning that your pattern matching is not exhaustive. So I think that's already one benefit that we can see from it. And the way we use this error handler, we might have some arbitrary I/O computation, in this case, a CAT's effect I/O, that can fail with any throwable. And we only care about handling errors of payment errors type. We don't care about any other throwable. So what this is saying, like this payment error handler of I/O handle errors, we pass the I/O computation, is that we are interested in handling the errors of payment error type. If there is any other exception or any other error being raised in I/O, we just let it crash, and we might just take care of it at the top level of the application or not. But that's very specific, that we only care about payment error handling. And again, if you're familiar with the hierarchy of type classes of CAT's effect, I/O already has a monad error instance of throwable. But here we are requiring a monad error instance for payment error. So again, the Scala compiler will complain, and this will not compile. But thanks to classic prisms in this case, we can make that compile and work. The mechanism is exactly the same. We just add a single import, and the magic happens. But if you want to understand what's going on under the hood, the mechanism is pretty much the same. We have this monad error of I/O and throwable. That's what we have using the I/O data type, so it's at the top level. So the library is smart enough to realize the payment error is a subtype of exception. Exception is a subtype of throwable. So it can derive an instance of monad error for you by creating prisms and accessing to the different branches of this co-product type. I think that's amazing. And then the example I gave, I only showed how to handle these errors, but I'm only printing the message into the console. It's not very useful. But one very interesting case that we make use of in production is handling business errors and returning the appropriate HTTP response. I don't have time to go through it right now, but if you're interested, I wrote, okay, I forgot. This is how it's the implementation of how you can derive the applicative error instance. Yeah, you can look at it. It's the same pattern. We just basically use the parent, recover with, and by using this prism, we can access the right branch. But I was saying that if you wanna handle business errors and converting them to the appropriate HTTP response. I wrote 2 extensive blog posts on this technique using HTTP4S, and I gave a short talk at Scale, by the way, last year. So you can check it out, or just ping me on Twitter or on Gitter if you have any questions. So far, so good. I talked about MTL and classy optics. These are very powerful tools, very abstract in a sense, but we as developers need to write enterprise applications. We need to deliver business value. And one thing I became a fan of is the Rio monad. The Rio monad, it's a package called Rio in Haskell. We have one simple Haskell service at work, and I make use of this package, which is basically a new type that it's a reader T plus IO, basically, as a new type, so you don't need to use monad transformers. And there's a whole design pattern around this. It's called the reader T design pattern. There is a blog post by Michael Sneumann, so I totally recommend it. And it's compatible with all these MTL type classes. What does that mean? It means that we can write 100% polymorphic code. And at the end of the world, we can materialize our program using Rio, which is this new type. Or you can do a combination of both, which is exactly what we do. We write some polymorphic code in very specific areas where we care about parametric reasoning and being polymorphic. And in the rest of the program, we just use Rio directly. The benefits are that onboarding newcomers into this kind of code base, it's much quicker. They don't have to learn many techniques. They only need to understand that with Rio, you can just carry some environment, and that environment can carry some state as well. And that's all you need. And it works, and it's easier to learn. This is in Haskell. What about Scala? So Scala, there is this library called Zio, which is a trifunctor, and in the latest version, allows you to carry some environment as well. So if we just new type that, we fix the error to throwable, we can get the instances for cats, and so we can make it compatible with all the cats ecosystem, so we don't miss out from using wonderful libraries like FS2, Doobie, and HTTP4S. It's called now Task R, by the way. Task R because of reader. But when I was playing around, I just defined a new type to match it with the Haskell equivalent. So let's see how we can make use of it, of this. Coming back to our example, in this case, I encoded our functionality as case classes, but it's exactly the same, asking for the current environment, and then printing that out to the console. Exactly the same, we are using applicative ask and classy lenses to derive the different instances. And then we have this program that instantiates the 3 different programs. And normally, the way you use MTL type classes is by materializing them using monad transformers, because we need that our type constructor F in this polymorphic version at the top, it needs the effect of carrying some environment. And normally, you will use Gleisli to materialize this program. Gleisli of task in this case, and then we can run, we feed it the configuration, and we get a task back. But since we have a new type right now, we don't really need to use monad transformers. We can use Rio directly, or task R. And instead of calling run, we call provide, and we feed it the configuration. So I think this is a great discovery for me, and I think it's one thing that I will probably give it a try in my next project. So in this small example, I just demonstrated that we can use MTL, we can use it, in this case, just applicative ask, classic lenses to combine, write 100% polymorphic code, and we can materialize that using the Rio monad, which is just Zio under the hood. So I think this one demonstrates that Tagless Final is not really dead. How many of you think Tagless Final is dead? Where's John? All right, I just want to bring it back to life, because I still believe this is a very powerful encoding. This is your photo opportunity. And so, but yeah, anyway, I understand the benefits. I also understand the drawbacks. It requires you much more knowledge. Onboarding newcomers or new people, it's much harder. But I think it pays off at the end of the day, because we are all functional programmers. We are interested in learning more and more. And I think that's great to see in junior developers. When they are really interested in this, it's because they want to learn more and they are hungry for learning. And I really appreciate that. And we normally hire for potential, not for knowledge. So if you demonstrate potential and you want to learn more, I think this is great. It's great in coding. But I would like to give some personal recommendation and advice of what's been working very well for us. This is like kind of like an experience usage report. I just show MTL, classy optics, and Rio, but we only use a small subset of these tools because they are super powerful. So normally we just use applicative ask from the type classes of MTL, eventually just monad chronicle, but in very small cases. And we handle errors using applicative error or monad error because that's the standard in the CATS ecosystem. And using classy lenses and classy prisms to derive such instances. That's been working very well for us, so I can recommend using this. Also, encode your effects constraints as implicit. What do I mean with effects constraints? I mean a console, a timer, a clock, and so on. But whenever you have business interfaces or business algebras, encode that explicitly. Say a user service, a product service, a login service, and so on. Encapsulate your state in interpreters. Your interface doesn't need to know anything about your state. That should be delegated to the interpreter. And I normally recommend using an atomic reference, just a CATS effect ref, or the equivalent in the other libraries, to carry state, because it supports concurrency. So if you use just state T or state, it can only thread state sequentially. And create modules for your dependencies. So in last Sean DeGau's talk at Tagless Final, he showed this example. Please don't do this. And this is horrible, it's terrible, and any pull request review should be rejected, like if you see something like this. So please don't do this kind of stuff. If you see like what I recommended, you have some business interfaces here encoded as implicits. Don't do that. Instead, create some modules to organize your dependencies, and you will end up with some function like this at the bottom, more or less. There are best practices, how you can encode, and by basically creating modules. Scala has a great support for modules, so that's what I recommend. And that's all I had so far. But since we have some time, I have some bonus slides. Who wants some bonus slides? Yes. All right. Let's get into it. I have to go a bit quicker on this because we're not going to have time to explain everything. But basically, what I just shown, MTL, classy optics, Rio monad, and how we can create big applications in the enterprise. So I was playing with an experimental feature or just an experimental design, basically. Instead of carrying this environment and creating our dependencies using this trait mix scenes, which actually is great reminiscence of the cake pattern that we left way behind in the past. So I say, what if we can just make use of the MTL type classes, applicative ask, to carry this kind of context, and classy lenses to let our functions know what they can access, what kind of data they can access, whether they can access to a cache, or they can access to a whole module, or just a user service, service 1, service 2, and so on. We can restrict these functions using classy lenses and applicative ask. So I play with this in an experimental design. I created the dependency graph, and basically we end up with this kind of encoding, this program 1, 2, and 3, but we already see an issue here. If you look at the program 3, this is becoming too large already. And because we are encoding again our business interfaces as implicit, in this case it's just an applicative ask, but it's pretty similar. So one way to get around this problem is just refactor it in this way. So basically creating an object with an apply that has all these applicative ask instances, and it can actually create the program2 class, which it will receive the business algebras as arguments. Right? So this is one thing that has been working well, but this is just totally experimental, so big disclaimer there. And if you paid attention to the way I define the applicative ask instances, it uses F for the reader effect, but also F for the effects that we're going to be running in the application. And normally these two should be different. The first one should be an effect able to carry some effects, where the other one should be a total effect with no ability to carry any context. So I got around that, defining this natural transformation from Rio or task R to task by calling provide from Zio. By having this implicit natural transformation, I can derive an applicative ask instance for task. I don't know whether this is lawful, and maybe people would shout at me, "No, that's wrong." Well, but I like to, I like to hear that, and probably that's what I put in the subtitle. That is totally experimental, so I don't know how lawful this is. The only thing I know is like it works fantastically well. So go ahead and check out the code, all the examples I've shown, complete the examples on different approaches. It's all in this GitHub repository. So that's all I had so far. Thank you very much.